Now you have already gone through the VQ sensitivity, then QV modal analysis. Then as an extension of QV modal analysis, you have this participation factor. Now the fourth aspect of voltage stability is the shortest distance to instability. How can you term the shortest distance to instability otherwise? Margin of stability, right? Or stability margin. What is stability margin? Anybody? What's the reference for stability margin? You have already studied the PV curve and right. So at present the machine, the system is loaded by some power in terms of active and in terms of reactive power. That at present the system is under some loading. So some P0 and some Q0 is already there according to the current state of the system. At present the machine is the system is loaded at P0 and Q0. Now how much can P0 be incremented by delta P and how much can Q0 be incremented by delta Q to touch the unstable point, or beyond that the system would be unstable. So that is stability margin of the system. That is the importance of stability margin of the system, or the shortest distance to instability. Now, so the smallest stability margin is to be found out. That is the shortest distance to stability. So let's take an example and see. We have a source connected to a bus and a transmission line. This is a radial system. Okay, so you have some PQ load. Okay, now if load increases, what does that mean? Load increases beyond a point, suppose beyond a point, then the system voltage will go down, right? And beyond a point, that means beyond a point the voltage becomes unstable. So this we want to know, or we want some information about this, how much the system can be further loaded. Okay, so what happens with the PV curve? I have already explained about this. When P is increased, voltage is dipping, and at this point, this is the collapse point, right? Collapse point, and at the collapse point, if you draw a tangent, it will be parallel to the vertical axis, and dou V by dou P would be infinity, and dou P by dou V would be 0. So inside the Jacobian matrix of the Newton-Raphson load flow, or the Jacobian of the load flow equation, in one element is JPV, right? So this JPV will become 0. So there are chances of Jacobian becoming singular, or the determinant of Jacobian becoming 0, and then it will not be invertible, right? Invertible. This Jacobian will not be invertible. So the load flow will diverge. Load flow will not converge. So when the loading reaches a point near to the collapse point, at that point itself, somewhere here itself, the load flow starts diverging. So after that we get a collapse. So this is just a mathematical region. This is just a mathematical region. We don't have a practical region here. Okay, as per equations, we get such a curve, but beyond this operating point, somewhere near to the collapse point, the system won't operate. From that point, it's direct collapse, the voltage collapse. So here also, the active power delta P to which the system can be further loaded. We should know about, we should have the information about this to know the stability margin. So let's see this with the help of a PQ plane. Let me draw it. I have a PQ plane. Okay, so this is Q and I am representing this as Q load because I have already considered the radial power system where a PQ load was considered, right? A PQ load was considered here. A PQ load was considered. So this is Q load and let it be in per unit and this be P load in per unit. Now I have several markings here. Okay. Now suppose I have a surface like this, beyond which the system is unstable. Unstable in the sense voltage unstable. Okay, voltage unstable. That means if I am starting with some operating point, initial operating point P0 and Q0, then I am increasing the loading of the system. So increasing the loading means increasing Q and increasing P. So it's increase of a vector, right? That means P and Q are orthogonal here, right? P and Q are orthogonal. So how much Q is increased and how much P is increased, accordingly the loading is increased, right? So the direction of loading is also important here. It can be increased in this direction or this direction or this direction or in any direction the load can be increased according to the increase in P and increase in Q. Now to find the shortest distance to this surface, this is a surface in the PQ plane, right? This is a surface in a PQ plane. So we need to find the shortest distance. Shortest distance to this surface. Okay. Now for that, how will you find it? So P0 Q0 is the initial operating condition and load PQ is increased from this point such that it reaches the surface S. This is S. Any point on that surface, if subjected to any point on this surface, if subjected to disturbance, it will go unstable. The system will go unstable. Okay, so we are trying to, 1 minute, let me erase this. Okay. Now, randomly I am drawing I'm increasing the power to this surface, up to this surface. Then I'm drawing a normal from this point. Okay, so this is some eta 1. This normal is some eta 1. So till point 1, this is point 1. Till point 1, I am increasing my loading from the initial condition P0 Q0, and from the surface at point 1, I am dropping a normal. Okay. Now, parallel to this normal eta 1, stretch the load again from the initial operating point. I am coming back to the initial operating point and I am stretching the load again parallel to this eta 1. Okay, parallel to this eta 1. Then it reaches the surface through another path. Okay, another path at some point 2. Now again I am dropping a normal from here. Normal in the sense normal to this surface. Okay, normal to this surface at that point. Then again I am coming back to P0 Q0 and again I am drawing. See here it has already almost reached the I mean shortest position. If I am going like this, then this will be the next normal eta 2. Then I'll again come back, right? I'll again come back. Then in parallel to N2 eta 2, I'll again go, right, and reach the surface. So this is an iterative procedure. This I'll do till I get the smallest distance. So we represent the initial operating condition by some vector rho naught and the final operating condition be rho star here in this surface S. So we will get this one, the norm rho naught minus rho star norm would be minimum. So each time when you stretch the load, you are getting some rho star. Rho naught is same. Now you will again come back. You will again stretch the load in the direction parallel to the normal, which you have drawn before. Like that you will draw, and finally you will get some norm which is minimum, rho naught minus rho star, which is minimum. So this is how we find the shortest distance to instability.